Allô? Allô, Émile?
Ah, oui, je pense que ça marche.
À tout de suite.
Allô?
Les autres s'en viennent.
Ça devrait, ça devrait. Juste en profiter pour dire que techniquement, je suis seulement inscrit au 2e cours.
Ah, OK. Ben, c'est comme tu veux. Tu peux rester si tu veux ou non.
Ça va me faire plaisir de rester. Je pense que j'ai besoin de ce rappel.
OK, ben c'est...
Juste pour voir si ça ne dérangeait pas dans le cours en tant que tel.
que tu sois là au lieu de pas être
Ouais,
là? Non, non, non,
exactement.
non, 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 non. Mais sache que je vais parler beaucoup.
Il n'y a aucun problème.
Je vais parler beaucoup en supposant que tu ne l'as jamais fait.
Excellent, c'est bon.
Bon. C'est Julien qui vient de rentrer. Bonjour, Julien.
Allô?
On attend les autres. Qu'est-ce qu'il y a, Lulu? Qu'est-ce qu'il y a, Lulu?
Allô?
Hello.
Hello again. Can you hear me?
Yes.
Good.
Who's missing? Who's missing? Oh, Elahe. Okay. Okay. All right. I have a link for you. Yes, I'm going to send this in the chat window. Whoops. Aha. Here's Elahe. Okay. There's a link to my slides, just in case everyone wants to have the slides directly. And you're also very welcome to translate them as I say them. I tried to translate a few, but good Lord, is that a lot of work. So it's going to be the same strategy as last time. It's going to be, I'm going to have Franken slides. I'm going to be speaking in French, speaking in English with slides, sometimes in English, sometimes in French. Is that okay?
Yes.
Okay, we're in business. So I sent you the link in the chat, but I will still show you everything on the screen. If I can get to my screen. Where is it? No, yes. All right, this one here. And I'm gonna start sharing my screen. This one. 1, 2, 1, 2. And here we are. Okay, so can everyone see my screen?
Yes.
Yep.
Okay, so what's our plan? Okay, the last time we talked in very general terms about geometrical optics, and the reason we had to do that is that you have discussed with Antoine, and I wanted to give a brief overview. After talking to some of you, did we lose Vincent? Oh, no, okay. After speaking with a few of you, I'm quite sure that most of you want to know the details of the formalism on how to do these relatively simple calculations. So I know that Shadi, Valérie, and Elahe want to know, and I want them to know. I know that Emile already knows most of it, but we'll get a refresher. How about Vincent and Julien? How do you feel? How do you feel in terms of in this optics class? Do you want to be able to do some calculations? Small calculations. Would you like to know, even if in the end it may be it may be that it's a bit too complicated? How do you feel about this?
I want to learn everything.
Yeah.
Everything, absolutely
Everything.
Okay.
But yeah, so I would like to try and do as much calculations as I can.
All right. So the plan then will be for now. Whoops. Okay. Okay. So the plan for now will be to go through the formalism, and I do that in my optics class in second year in physics, but I have a shorter version for you guys because there are some basic things that I believe you already know, but we'll see how it goes. But my plan is to do a little bit of formalism, examples, a little bit of formalism, examples, and then I have a fairly let's call that a summary question for the assignment that is more complicated. So it will include all the details that we'd like to know. Okay, so the question, actually, I have if you really want to see, I have, where is my question? My question is going to be here. Where? It's gone. Yes, I have a question related to, yeah, it's right here. Now you don't see it, but whoops. So the question that I have for you is that this is a complicated microscope, but that's a real microscope. And I want you to tell me what the field of view of this microscope is. So that's my question. That's an extremely simple question, but it requires a little bit of simple math. So that's what we're going to get to. Okay, so now I'm going back to my slides. There we go. Okay, so so what are the objectives for today? I want you to understand the details of ray tracing, and ray tracing is more general than imaging. So when you do imaging, what you do is that you have an object and an image, but I'll show you how we can do everything in between with this formalism. And everything in between is very often what we want to do in our own systems. So this is called the matrix formalism, or ray matrix formalism, or ray matrices. And so today, okay, how come I know? Oh, my pen here like this. Okay. Hey, how come I don't see what's going on here? I don't see my pen is not working. That's no good at all. Just give me a second. My pen. Oh, okay. There we go. Okay, I got it. Okay. Yeah, all right. Okay, sorry. Everyone can hear me still? And everyone can see my screen? Excellent.
Yep.
Okay, so the matrix formalism, we will define what it is, and I will show you how we can use this formalism to propagate rays. It's very simple. And then we will look at how we can use this formalism to look more generally at lenses and optical systems. Okay, so we'll describe a critical parameter called the principal planes, and we'll figure out how to find them, what they are, and how to find them. And we'll calculate the equivalent focal length of an optical system, and we will use the formalism to repeat what we already know from imaging. We have the regular equations for object image for a given focal length, but now we'll be able to do that for any optical system. Okay, and then we will the goal will be to use it to solve a more complicated problem. So you have done this before. This you know. Okay, this you already know. You know that what are we looking at here? Okay, you know certain rays that you can trace in a lens. If a ray is parallel to the axis, then it goes through the focal length, the focal spot, sorry. So it will cross the axis one focal length after the lens. That's a definition. Okay, we know that. Then if it goes through the focal spot, it will come out parallel. And if it goes straight through the center, it's essentially not affected. So you should know that. So is this known for everybody?
Yeah.
Yeah?
Mm.
Sure?
Yes.
Okay. So this we know, and from these rays, we have, or you have, you know that sometimes if you have an imaging system, you trace several rays. You see that I traced our 3 rays on this graph. One is parallel, goes through the focal length, the focal spot. One goes through the center and then straight through, and one goes through the focal point on the other side and comes back, it comes out parallel. So all the rays they all start from the same point, and they cross at another point, and it's all the same point. They're all crossing at a single point. So that is the definition of an image, because all of the rays that are originating from this point, all of them in all directions, if they go through the lens, then they all go to this point. Okay? Remember that, because I have a question in about 5 minutes that this will be relevant. Okay, so we do this, let's call that intuitively, because we've used the rays that we knew. But, and with this, actually, we are able to do a lot of things. We can define the magnification of a system. Okay, we can define the magnification, and the magnification is the height of the image here compared to the height of the object here. And in this particular case, it depends on the distance, the distance between the lens and the object, and the distance between the image and the lens. No big deal. And we have equations that you have seen with Antoine, with me last week, and before in Cégep and in college, and maybe even in high school. So far, these are all things you know. Okay, this equation you've used before. So, and when you know the object and you know the focal length, you know the image. And most of you probably know the lens maker equation. Who recognizes this? What's the purpose of the lens maker equation? Why do we use the lens maker? Okay, anyone has seen the lens maker equation before?
Yes.
Yeah.
Yeah. So what do we do with the lens maker equation? I'm waiting. We get the focal length of a lens. Okay, the point of this equation is it tells you that if you know the index of refraction and the radii of curvature, so if you have a lens that has a certain curvature, a certain index of refraction, then you know the focal length. And then there's a super general version of the same thing here. So this here is for a simple lens that looks like this. and you have a certain radius of curvature for one and a certain radius of curvature for the other. But then there's a very, very, very general version that will depend on the index of refraction on one side, the index of refraction on the other inside, and the index of refraction outside. Well, all of that is you could learn all these equations by heart, but you'd be crazy. Okay, well, sometimes it is good to know these equations, but it would be nice to have a strategy to do that is more general. Okay, a strategy that works for any situation, and that's what we're going to do now. So the one thing that you need to essentially accept is that there are many ways I can say this, but let's go for the simplest solution, the simplest explanation. And if you have questions, just raise your hand. But in the most general strategy, the most general description of any optical system, we have a ray that goes in a certain direction. It makes a certain angle with the optical axis, and it is at a given height with respect to the optical axis. It's going to go through something, whatever this is. It doesn't matter if we know or not, okay? There's something. And it will come out at a new height and a new angle. So that's as general as it gets. There are only two parameters. Where is it in height and what's the bloody angle? That's it. There's no wavelength. There's nothing else. Okay, these are the only two parameters that we have. So because we only have two parameters, and because we know that the materials are simple materials, we know mathematically that we can express that this is a very important equation. Do you see that the output height has to be a combination of the input height and the input angle? And the output angle has to be a combination of the input height and the input angle. So that's really as general as it can be, because it's like a linear fit. You know, you can only have an expression that's going to be a fraction of something times the fraction of something else and add them. Okay, it cannot be more general than that. So now you may be thinking, okay, why would I care? Okay, why would I care? The reason we care is that who remembers matrices from college and math? And Vincent, Julien, Valérie, how's that? Yeah? Julien, not so sure?
Not so sure, no.
Not so sure? Okay. So it's not difficult. So it doesn't really matter actually. You'll see that it will become very natural. We define a matrix that is a column. So this here or this here, it is the ray. So the ray is a column matrix that has the height and the angle, the height first, then the angle. And then we will define matrices that will define any optical element. So we will see in a second on the next slide, what is the matrix for a lens? What is the matrix for free space? What is the matrix for a bunch of things? But for now, we just call them matrices, and it's going to be A, B, C, D. So we just say it has A, B, C, D. Do you have a question, Shadi?
No.
Okay. I thought you were raising your hand.
No.
Okay. So what we'll do, the reason why this is important is that, do you see that if this equation is true, and I'm telling you that it is true, then you can write it as a matrix multiplication where you have the matrix for an element times the matrix for the ray. So then when the matrix is applied onto the ray, then you get the output ray, and it is given by this expression, which we said is fine. So does that make sense, Julien? Yeah?
Yeah.
All right. So the reason why this will become interesting is that once we have transformed this ray, so now we have a ray that is transformed, we can transform it again with another matrix. So what we will do is that we'll have a matrix that will, say, propagate the ray in free space, then go through another matrix that goes through an interface, then propagates in another material, and then another interface, etc. So then we will show that every single thing in my optical system, because it can be described by a matrix, I can multiply all the matrices and replace tons of things by one nice matrix that is just 4 numbers. And there's enough in that matrix to extract a lot of things about the system. So the advantages are numerous. It's very, very advantageous because, first of all, it formalizes the ray tracing task. Because now ray tracing, instead of being let's draw lines, let's just draw lines on the on a figure, then we can just say let's take a ray and propagate it with all the matrices, then another ray and propagate it, then another ray and propagate it, and then we can propagate as many rays as we want to get an idea of what's going on in the system. And I'll show you that we can actually use this matrix to find the imaging planes and the conjugate planes, the limiting area in a system, etc., etc. Okay. So it formalizes the ray tracing task. The second thing is that it's highly suitable to a computer implementation because it's so straightforward. That's really my fourth point here, but everything is very straightforward. You're going from here to there and the elements, well, then you can just propagate everything. And it will allow us to redefine the optical elements with terms that are more general and will allow us to take a very complicated system and transform it into something into, let's say, we can take a very complex lens like an objective. A microscope objective is an extremely complicated lens, but then we'll just say, yeah, blah, 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 blah. I don't care about the details. It's as if this was this other lens that I'm now describing that has a focal length of this and principal planes here. That we're going to describe something called principal planes. But the point is that we'll just say, yeah, it's just like a simple lens. Okay? All right. So let's start, and you'll see we start with extremely simple things at the beginning. Okay, so let's say I have a ray and I want to propagate it in free space. So I have a ray. Look at this here. I have a ray that is at a given height, at a given angle. If the ray, so very, it couldn't be simpler than that. So if this ray is propagating in free space for a distance d, what is the resulting ray? Well, it's not particularly complicated. It's super fancy geometry with a triangle like this. There's a triangle here, here, like this. So we know this angle here. We know because that's the input angle. So this height here will be what? The height, the final height, the matrix that will describe this is the following, because we have the final height is going to be the input height plus theta times d. Now, maybe you're thinking, how did we get theta times d? Who remembers, you know, these triangle, sine, cosine, tangent, everything? How does this work?
It should be times sin theta d.
Exactly. So sine, I'm not writing particularly well. Let me start over. Okay. So if we have a triangle like this, we have theta, then sine theta, if we have y, d, and let's call this h, sine theta will be
Y over H.
y over h, cosine theta is d over h, and tangent theta is y over d, okay? But we are assuming that the angles are small. So when the angles are very small and we use radians instead of degrees, so we always use radians in physics, then we can say that sine theta, sine theta is essentially very close to theta. So here, instead of doing that the output height is y plus sine theta times d, we just say that it's almost the same as y plus theta times d. Okay, we could have used sine theta, but we use theta for tons of reasons, and for now, that's what it's going to be. Okay, it's simpler. Okay, so the matrix, then what does this mean? This means that the matrix here for free space, if I know a ray, and the ray is propagating in free space for a distance d, all I need is to describe the matrix that we apply to that ray as 1d01. Of course, the angle, so the height of the ray is going to go from here to here. So we say the matrix transforms the ray after it has propagated by a distance d. The new height is going to be y, y plus theta d. And what is the output angle? If I had an angle of theta at the input, what's the output angle after a distance d?
The same.
Yeah.
Same? Same? Yeah, everyone see. There are two things here. The first thing is, obviously, we know that if it's going in free space, it's not going to change direction spontaneously. The second is, mathematically, how do we see that? The multiplication is here, okay? So we multiply, I'm running out of space, okay? Okay, we multiply, whoops, we multiply, there we go. We multiply, and then we get that theta prime is equal to 0 times y plus 1 times theta, which simply means theta. So far, so good? So matrix multiplications. Valérie, Vincent, Julien, yes, no, not sure? You're not sure, Vincent? So unmute. Go ahead.
Yes. No, I don't quite remember.
Okay. So we'll look at it. We'll look at it a different way. Okay. This part has no matrix multiplications. No, this is just something is equal to something times something plus something plus something. So there are no matrices here. Huh? And same thing here. The angle, the output angle is C times the height plus D times theta. So if you accept that this is what we're trying to do, then you can remember by heart that when I apply a matrix to a ray, this is the, this is the equation that I get. Okay? So so it's AY plus B theta, and the output angle is CY plus D theta. Okay, so there are other details with the matrices that that we can use, but for now we won't. Okay, so okay, I really want to get to the details, so let's move on. The second, that's the most important, and that's really the only one we need to know, is what happens to a ray that hits an interface with a curve. So we have, if a ray is propagating in space, we have this very simple relationship. And then if a ray is hitting a boundary, it is coming from a certain index of refraction n, and then it goes into another medium that has an index of refraction n2, and it has a certain radius of curvature. So in this case, if the curvature is like this, we say the radius of curvature is positive, and if the curvature is the other way, we say the radius of curvature is negative. Okay, it's not particularly difficult to prove this this thing here. I will not do that, but you have to see that, whoops, it is just drawing and geometry. Okay, we know that if the ray arrives here at a certain angle and then it hits this at a certain height, because we know the circle, we know what the angle of the circle of that the interface will be, so we know the angle of incidence here. And then we know, if we know the angle of incidence, let me do it again. Up. If we know, yeah, okay. Let me do it like this. Yeah, okay. So we have this. So if a ray hits at a given point, we know the height and we know the angle. So if we know the angle here, we will know the angle of this interface, and we can calculate the angle of incidence, and then we know the law of refraction. So the law of refraction we know because we discussed this last week. I asked you and you told me n1 sine theta 1 is equal to n2 sine theta 2. So you know that. So if you have the height and you know the curvature because you know the radius, then you know exactly the angle of incidence and you can calculate the angle of refraction. That's all we need to have to calculate absolutely everything in the world of optics. Okay? And just because we know that, that doesn't mean I will not show you one more, but please understand that with this, we can do everything. Okay? So the matrix for this, for a dielectric interface, so a ray coming from a medium of index n1, entering a medium n2, at a given height, at a given angle, and a radius of curvature r is given by this matrix. Oh, good Lord, let's look at it. It's a little bit complicated, okay? But let's see. It depends, if you look here, okay, it depends on the index of refraction inside, the index of refraction outside, and the radius of curvature and the index of refraction inside. What do we see? Okay, and then here there's the ratio of the indices of refraction. Let's see, what happens if the index of refraction N1 and N2 is the same? What would happen physically if N1 is the same as N2? Let's say I have a sphere with an index of 1.5, and I'm coming from another medium with an index of refraction with the same value. What do we know will happen physically if it's the same index of refraction on both sides?
Nothing happens.
Nothing happens. Is Shadi right or wrong? Valérie, I want answers. Valérie, is she right? We're not sure. Is she right? Valérie?
I'm thinking.
Uh-huh. Well, Julien will help you think. Julien? So let's say this here is an index of 1.3, just like water.
I think still absorbs some light.
We're not talking about absorption here.
Okay.
There's no absorption. We're just, the only thing we're doing here is light is refracting. We're only considering the index of refraction. So Julien, so the index of refraction here is n, and inside it's also n. So there's some curve, but they have the same index of refraction. So what happens?
I think I would say nothing also,
Nothing.
but with the curve, I'm not sure if it's true.
Mm-hmm.
So
yeah, okay. So we have 2 nothing, 2 nothing. 1 I'm thinking. Vincent has a muting, and Emile knows, so he's not saying it. And Elahe, what do you think?
I think if the curve doesn't have any parameter in the M matrix, if we put both N1 and M2 the same N, so for the angle it will be 0 and 1, so nothing happens.
Okay, so 3 answers here. Elahe said, let me just do the matrix. Let me just calculate the matrix. So Elahe is an engineer. She calculated the matrix. So she got 1, 0, N2 minus N1. I told you it's the same value. So that gives 0. And then N1 over N2, that's 1. All right, so the matrix here is 1, 0, 0, 1. So if I come with an angle, a position y and theta, the output, if I multiply this, so it's a times y, b times theta, and c times y, d times theta for the output, we get y and theta. So the height does not change and the angle does not change. Okay, matrices. Okay, well, let's just do, my name is Vincent 2, and I'm not so sure about matrices. Okay, but I know refraction. I know refraction. Okay, so what if we had used this? Okay, so there was some incidence on some interface, and we're not too sure what that angle was, but let's assume, okay, I hit this interface at whatever angle. Let's call it alpha. Whoops, alpha. I don't know what it is, but it's alpha. Okay, and it's the same index on both sides. So we have N1 sine alpha is equal to N1 sine theta, and it's the same N, and we're looking for theta 2, and we have theta 1. Okay, let's do a little bit of math. Okay, tiny little bit of math. Okay, I'm going to do it on the side here. Okay, so N sine alpha is equal to N sine theta. It's the same N on both sides. Sine alpha is equal to sine theta. Alpha is equal to theta. Alpha, the angle has not changed. Okay. Cha-ching. And then again, you may have known anyway that, you know, if there's no change in index of refraction, you know, the only thing that makes rays refract is when the indices are not the same. So even physically, that was another explanation without math. Okay, so we had 3 ways of thinking about this. Okay, is everyone satisfied with at least one explanation? Yes?
Yeah.
Valérie?
Yeah.
Valérie? Yeah? Your yeah sounds like a yeah. Why are you not sure?
I don't know. I don't know.
Okay. Okay, well, we'll keep going and we'll see how, if it gets more complicated, we'll come back. Okay? All right. So what do we have? Okay, what do we have? We have free space and a curved interface. And it doesn't matter how we got to the details, but we ended up with a matrix that will describe anything hitting an interface like this, and a matrix that will describe a ray propagating in free space anywhere. Okay. Yeah, all right. Okay. There's one final one that we'll do, although we wouldn't, in theory, we have enough with these 2 matrices to do everything, but we'll still do one, okay? Because it's very convenient. But we have a matrix for a thin lens, okay? And what do we know about the thin lens, okay? If we have a thin lens, if we have a thin lens like this, we already know, because we drew that before, that if light comes parallel, it will cross here on axis at the focal spot. And if it comes, if it comes through here, then it's going to come out like this. And if it comes, my finger keeps touching my keyboard. Let me remove this and see what happens. Okay. Let's see how that works. Up, up, lens, up, zoom, 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 and then here like this. Is that good? Okay. What I'm saying is the matrix for a thin lens is going to be given by something like this. What is a thin lens? A thin lens is a lens that really has a focal length and nothing else. It acts instantly on the light and will just bend it like a lens we know. So if something comes parallel, it will send it to the focal spot. So for instance, if we had a ray that comes parallel and we want to see where it's going to cross the axis, how would we do that? So I have this. I want to show that a ray that comes in parallel with the optical axis will cross at the one focal distance away from the lens after the lens. How do we do that? What's the strategy to solve this problem? We have, I'm going to take another program for this. No, not this one. I'm going to take this one here. This, okay. Okay. So everyone sees? Yeah, okay. So we have, today we have, maybe a bigger pen. Okay, anyone has an idea how we're going to do that? So I have this. I have my matrix for free space. I have a matrix for interface, and I don't remember what it is, but I think it's N2 minus N1, N2R, N2, N1, 1, 0. I usually don't know by heart, by the way. I look it up all the time. But we're not going to need this one. Okay, we're not going to need this. And then we have the thin lens, and the thin lens is 0, 1 over F1. So free space, lens. And now I have the following problem. I have a lens, and I have a ray that's coming here at a given height, y, and a given angle. What's that angle? If the ray is coming like this,
0.
0, excellent, 0. And I want to know what happens. I want to know what happens on the, we know, okay, let's see. Let me say it differently. A ray that comes parallel to the axis, we know what happens. What happens?
It passes the focal spot.
It will cross the axis at the focal spot. That we know, because you told me before. Everyone told me before. You knew that, right? Okay. So now I will show you that if we have the matrix for a thin lens, we can calculate that very easily, and that's what I'll do with you. So are we ready? How do we do that? Okay, how? How?
We can calculate the angle when it passes the lens and see the place that it moves from the.
Okay.
Yeah.
This all makes sense. I like that. I like that. So Elahe said, we'll calculate the angle of the ray after the lens, and then we should be fine. So Valérie, what do you think? Is Elahe just confused? What is she talking about?
But I don't know. I would just multiply all the matrices together.
Okay, not
We've
bad,
seen
not
that
bad.
R2 equals, what is it?
What, R2? Did you say R2?
Well, the second ray after passing in the lens.
Okay, so let's write down. There are tons of ways to do this problem. I think Elahe has a good strategy. I think Valérie has a good strategy too. So the first part is, we said array parallel. I said array is coming parallel to the axis. So did I say where the ray was? At what distance from the lens? No. Does it matter?
No.
It doesn't matter, because if it's at a height y and theta, it's going to hit the lens at a height y and an angle theta. And we see that fairly easily, because I'll just write the matrix. I'll just do, let's assume it's at some distance x that I don't know anything about. Then if I have a ray, what happens to a ray that is y and 0, because it's parallel? What's the answer? It's x times y times 1, that's y, plus 0 times x, that's 0. And then y times 0, that's 0, and 0 times 1, that's 0. Well, of course, we're not surprised. A ray that is parallel at a given height will stay at that height at the same angle all the way to the lens. Okay, so we have the first part. We have the first part, so I'm going to delete this just to make sure I don't run out of space. Okay. Oh, I can do this. This is so convenient. Okay. So I have this. So it doesn't really matter. So we have our lens, our ray at the lens. It's y and 0. Okay. And then what's the matrix for the lens?
1, 0.
1, 0.
Minus 1 over f and 1.
1, 0, 1 over f. Okay. So my ray will cross before it's this, and right after it will be the multiplication of the matrix times the ray. So let's do that. I'm writing it out here. Okay. Let's see. Y times 1. Okay, again, just just remember by heart, Vincent. So it's this times this and this times this to get this here, the one here. So what do I get?
Y.
What do I get?
Y.
I get Y. Okay. Are we surprised?
No.
We're not surprised. The ray is hitting the lens, and right after, it's going to change its angle, but it's not going to teleport to a different height. It just hit the lens at that point. No big surprise. Okay. And then the second one, it's this times this and this times this. What do I get? What's the angle coming out?
Minus Y over F.
Minus Y over F. Matrix master Vincent. Excellent. Okay. Okay. So now the angle, what do we notice? If F is positive and Y is positive, the angle is negative. Okay. An angle negative is an angle going down. An angle positive is an angle going up. Okay. So far, so good. The ray is coming down. Okay. It's coming down at an angle. That angle here is minus Y over F. Okay. Where now, everyone, how a little bit of geometry. Okay. So if I know the height here, and I know the angle. So where is it going to cross here? How do I figure out where it's going to cross here? There are two ways of doing it. The first one is to stop here and say, oh, come on. I know exactly what's going on. This is a triangle like this of height Y with an angle theta. And because this is parallel to this is the same angle theta.
Mhm.
So therefore, I'm looking for this distance, which I would love to know. And I know that tangent theta will be Y over that distance that I'm looking for. And we know that theta, okay, theta is minus Y over F. But if we assume, you know, if we just do positive angles because it's a triangle, we get Y over F. Yeah. So therefore, that distance where it's going to cross the axis is F. Hey, big surprise. Okay, so this, we did a little bit of geometry. Okay, just a little bit of geometry. There is another way of doing it that's a little bit, that's more general. And we can just, Valérie, that was actually Valérie's strategy. Okay, Valérie said, I'll just multiply all the matrices. I think that's a good strategy. So let's do that, okay? So we have essentially the same problem, but we'll just say, we'll multiply all the matrices. So the first matrix, okay, so I'll do this here. Second strategy. Okay, we'll just multiply all the all the matrices. Okay, the first matrix is the lens. Okay, so 1, 0 minus 1 over F, 1. And then I will propagate a certain distance that I don't know yet. I'm looking for that distance. So I'll propagate a distance D. Okay. And with this, I have my original ray. That's my, whoops. That's my ray Y0. Okay. So I have my original ray here. It's at a given height and an angle 0. And it goes, we write the matrices in that order. This one is applied first on my ray. then this transforms the multiplied or the transformed ray. Okay, so I don't have to I don't have to multiply the ray by the matrix first. I can decide to multiply the two matrices first. I can do what I want. You remember, 1 times 2 times 3 is the same as 1 times 2 times 3, or 1 times 2 times 3. It's the same. Okay, same thing with matrices. All right, so let's multiply the matrix. Okay, let's multiply this first, this matrix here, and this matrix here. All right, so I need someone to give me that answer as I do it here. So I'm just going to say this, I'm not touching the array. I just want to multiply these two matrices. How do I do that? What's the answer? Anyone? Yeah, 1
minus d over f.
Yeah. Then
and d. No,
yeah.
And it is minus 1 over f, and it's 1.
1. Can anyone see that?
Yeah.
Yeah. Like this. Everyone sees that?
Yeah.
Okay. So let's take just a few seconds to look at what we have. Okay. So what is this matrix here? What is this? Well, this matrix is the matrix that represents going through a lens and moving forward a certain distance d. So it has replaced these two things by one matrix. Okay, good. And I don't even need to know the details here, but I know that my ray, when it propagates through that, will be transformed by this matrix. Okay, so let me take all of this and copy that on another page. Up right here. Okay. All right. Okay. So what is, so I know that I started on, oops. I started on one side of my lens, and now I have propagated a certain distance d that I don't know. And what do I want after that distance d? That's the part that's important. What do I want? So Valérie, help me here. So what do I want? I have gone through my lens and I've propagated a certain distance d. What do I want in my problem? I said I want to know when the ray crosses the axis.
Yeah.
What does it mean with our matrices? Whoops. What does it mean when, what does it mean? What?
When y equals 0, the height.
Excellent. Okay. So this ray will do stuff. We'll get here. And I don't know what the ray is going to be here. Well, I do know certain things. I know that the ray here will have a height of 0, because that's what I want. And some angle, whatever that angle is. I don't know what that angle is. And I don't really care. I just want to know when is it crossing the axis. Okay, so what do? Well, I'll multiply this. I'll multiply my ray that is parallel by this big matrix, but I'm only interested in when it gives a y of 0. Okay, so I get y prime is equal to y1 minus d over f plus d times 0. Everyone sees that? I did y prime is equal to a y plus b theta, where this is a and this is b. Everyone sees that? Yes? Okay. Good. So therefore, what do I want? I want this to be 0, y1 minus d over f. And at this point, it's only math. But when is any y times something equals to 0? When is a product of two things equal to 0?
D over F is 1. Is it equal to 1?
Yeah, exactly. When this is 0 or when this is 0. And of course, if y is 0, well, that's not a surprise. If a ray is already on axis, it's going to stay on axis. So that's the boring answer. The one that is true for all rays is, aha, when d over f is 1, that's 1 minus 1, 0, then it's always going to be 0 after a certain d, and that d is when d is equal to f. Isn't that great?
Yeah.
Valérie? Yes? Is that great?
Yeah.
You don't look outrageously enthusiastically.
Well, we knew the answers.
Okay. But did you see how to use the matrix? Because this is the simple one, but we're going to do things that are more complicated in a minute. But we're going to use the matrix formalism. We're going to find principal planes. We're going to find tons of other things. We're going to show that certain systems are imaging or non-imaging. That's the second part. Okay, so we had a very simple system with only a lens and distance in free space. Okay, so let me show you something else. Okay, I'm going to go back to my slides. Okay, and let's just see. Okay, bear with me for just a few minutes. Okay, but you know, because you've seen that before, you told me before that you knew the lens maker equation. Everyone said that the lens maker equation you knew. What's the lens maker equation? I'm showing it to you again. It's an equation that if you know the index of refraction, the radius of curvature of both sides, then you can calculate the focal length. Well, let's try to do that ourselves, okay? Let's try to see, could we get that from the matrix formalism? Let me show you how we can get that, okay? So what we'll do is that we will assume that our ray, any ray, is entering something that has some radius of curvature. Outside, it's an index of 1. Inside, it's an index of n. And then there's another radius of curvature. So this one is R1. This one is R2. Okay? So I can calculate a ray that goes through an interface and then essentially no thickness, okay? We're just saying, let's assume it's a very thin lens. So it goes through an interface with a radius of curvature, and then right on the other side, there's another interface with another radius of curvature, okay? So how do we do that? Well, we start with, I did it for you here, okay? Look at this. You will be amazed. You should be amazed. I was amazed the first time I figured it out, and we're not even halfway through, okay? So look at this. So I took the matrix for a curved interface with a medium with an index of 1, a radius of curvature R1, and an index of a material N2. Okay, so that's the index here, N2. I kept N2 for simplicity, but I assume that N1 is 1. Okay, so I'm going through the first interface, and then right after, I'm inside my hey, someone is drawing on my figures. Okay, but that's okay. Where was I? Yeah, okay. then I go from my index, my medium with an index of n2, and back into an index, a medium with an index of 1. So now I am currently in a medium n2 going into n1, okay? So we just need to get the indices right. But so then I have this new radius of curvature. So what did I do? Here, okay, this is from outside the lens through the first interface. And this is from the inside of the lens and outside to the outside world. So R1 first, R2 second. Big surprise. Okay, multiply these matrices. Okay, I did that for you. Okay, I did that for you. I'm that friendly. Okay, look at what we have. Okay, so what did I draw? What did I have? I had a certain lens with crap, I lost it. Yeah. Yes, I had a lens with a radius of curvature R1 and a radius of curvature R2, like this, right? And I wrote the two matrices that represent both. This, we all understand. What is this? This is a thin lens. Of course, it's a thin lens. I did not propagate any distance here, and I just assumed the two interfaces were stuck to each other. Okay, so I multiply the matrices. What do I get? I get this. I get this. Look at this. I get this. Do we recognize this?
Mm-hmm.
Okay, because we said, what did we say? We say this is a thin lens. We know that a thin lens can be described by a matrix that is 1, 0, minus 1 over f1. We know, we just did that. And everybody nodded saying, yes, yes, thin lens. Okay, now I said, well, let's just assume that let's just do the math going through the first interface and the second interface, and let's just see what we get. Well, now we're doing all the physics because we have the curvature of the interfaces. And then we get an expression here that, big surprise, is we see that 1 over f is equal to n minus 1 times 1 over r1 minus 1 over r2. What is this? What is this? It's this. It's the Lensmaker equation. Of course it is the Lensmaker equation. Okay? Because we knew that a lens would behave like that, but if we know the radii of curvature, then we're not surprised. We can calculate the focal distance of a certain lens. Okay? You should be in awe. You should be saying, whoa. You know, I'm so impressed. Okay, and as I said, you haven't seen half of it yet. Okay, up. Let me see. Yeah, okay. So there you go. This is what I just showed. So if it is a thin lens, and I did everything with the radii of curvature, then I can extract or calculate the I can obtain the Lensmaker equation, because a thin lens for which I know the radii of curvature or the focal distance, I can either calculate the focal distance and just put it here, or just leave everything like this. Okay, of course, we don't do this is an academic example that I just did for you. If we have a thin lens in most of our systems, actually, no, let me rephrase that. In all of our optical systems, if I say, oh, we have a lens with a focal distance of 50 millimeters, you don't start looking for the radii of curvatures to write the whole thing with complicated terms. You just write 1 over f with 50 millimeters. Okay. All right. Okay. I'll do one more thing. I know I'm going beyond 1 hour for the first part, but the timing is good. Timing is good. Okay. So I'll just show you the second thing. Okay. I told you that the formalism we have. Okay. So far, is it too complicated? Especially Julien, Vincent, Valérie. How's that coming along? It's okay. You're in awe. You're thinking, I never thought matrices were so interesting.
Yeah.
It's really cool.
It's changing my life.
Yeah.
I know. You know, you've entered the matrix. Okay. All right.
I want more. I need more.
Oh, it's coming. It's coming. Okay. So let's look at this. I told you that it's more general than the imaging equation that you know. You know 1 over O plus 1 over DO plus 1 over DI is equal to 1 over F. You know that, right? Everyone knows that. Yes. Okay. Well, could I recover that equation with the matrix, all the matrices? How would we do that? So let's see, okay? Let's say, now I'm not interested in rays everywhere. I'm interested in rays. I have the rays. I have an object at a given point, a given distance, and I really want to know where the image is. So that's not the same as what we just did. We had a parallel ray, and we were looking at the focal, the focal point. That's not an imaging situation. It's just, we're just tracing rays and doing stuff, okay? But if I had a system where I want to know where the image is, how would I do that? What does it mean in a system, in a system like this? What does it mean to have a situation where I have an imaging condition? What does it mean? Tell me, how do we tackle this problem? So I will have matrices, and I'm really looking for this thingy. I want to know where its image is. What do I do? What do I know? What do I say? Help me.
In this situation, sometimes the theta is not 0. Yeah, and I guess we should consider a free space before length. Yeah.
What's the question?
The question is, okay, yeah, what? Very good, Valérie. What is the question? Okay, you know 1 over, you know this, okay, you know 1 over DO plus 1 over DI is equal to 1 over F. No one proved that to you. You were told that this is true. Correct?
Yeah.
Okay. And so that said, I told you the ray matrix formalism can do everything. It can cook, clean your house, and calculate ray traces everywhere. So I have to be able to use the ray matrix formalism to recover this equation. So if I have an object here at a, if I have an object at a distance DO from a lens, how do I, this is annoying. Like this DO. How do I figure out DI? So that is the question. You know.
You multiply matrices.
Oh, we'll need to multiply matrices big time. But what are we going to do? So let's multiply the matrices. But then what? Okay. So I'll multiply the free space matrix for DO. And that's given by my problem. I'm saying I'm putting something DO before a lens. Okay, so we know DO. We at this point it's given by the problem. Then I will go through a certain lens that has a focal length of f. Sorry, focal length of f. And I know that too. And I know the matrix. But then I'll propagate a certain distance di that I don't know. What am I going to do?
We can't hear you.
Huh?
Yeah, it's cut for approximately 10 seconds.
Okay. All right. Now can you hear me?
Yeah.
Yes.
Yeah.
Okay. It's I think the kids are playing Fortnite upstairs. And if they're all playing at once, it's complicated. So we will calculate the matrix for DO, which is very simple. And we have the matrix for the thin lens, which is 1, 0 minus 1 over f1. But then we'll propagate a certain distance di, and we don't know what di is. So, you know, before, when we did a simple problem before. Okay, we did a simple problem where we calculated where the ray was crossing the axis. We did that. We just did that. I hope you guys remember. That's 5 minutes ago. Okay, so what does it mean to have an image? Now, because earlier, Valérie told us, we said, oh, yeah, crossing the axis, that's when y is equal to 0. But we knew, you know, we had our problem and we said, oh, yeah. It's going to cross when the ray has a y of 0, then the ray is on the axis. But now, what do we do? What do we do here? How can I describe that this is imaging? What is imaging?
Well, it's when the three rays, I don't know, have the same position.
Say that again.
When the three rays.
Okay. I like that. I like that. Okay, that's
the same height.
What?
The same height.
Okay.
Not necessarily the angle, but the same height.
Okay.
Yeah.
Okay. I really like what Valérie is saying. So Valérie said the rays here, the rays are all starting at the same height. They all end at the same height. And then what did you say after that?
Well, they don't necessarily have the same angle, but...
Exactly. Okay. So for some reason, they all start at the same height. They may all have different angles, but it doesn't matter. They all end up at the same final height. Okay. Aha. Okay. So how would we do that mathematically? Okay. So we can multiply the matrix here, and here. So we can take the block of DO, F, and DI. We can replace all of that by a single matrix. We all agree with that? Yeah. Now you can hear me? Yep.
Yeah.
Okay. Yeah. When I see you move, I understand that you can see me. Okay. So we all know that we can multiply all of the matrices and get one single matrix that will be A, B, C, D, whatever the numbers are. I don't really care what they are. Well, I know on the next slide, but we don't know that whatever it is, we'll get the whole system replaced by a single matrix. Okay. So what would be, Valérie now, call the mathematician in you, and you said it doesn't matter, they start at a given height and they end at a given height regardless of the angle. Okay, so let's look at this. So what does it mean? You said you start at a given height, y1, and you will end up at a given height, y2, regardless of the original angle. Mathematically, how do we take this? Yes. Okay. Okay. That means that the matrix that represents the whole system must have B equal to 0. That is awesome. Okay. So when B is equal to 0, what does that mean? That means regardless of the incident angle, a given height will be transformed to another height regardless of the angle. That is exactly what I drew originally. I told you before. I said I'll come back to that. I said all these rays start from the same point with tons of angles, theta 1, theta 2, theta 3, blah, 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 blah. But I don't really care what happens in between. They all go to this new y2, regardless of the angles. No angle. Okay? Oh. Ah, okay.
Are
Now I
you
can.
okay?
Okay, good.
Yeah. I'm looking at everyone. You just have to go like this. When you cannot hear me, just go like this, because I can see you. When no one's moving, I know my internet connection is not good. Okay. So if for a matrix, the B element is 0, then I have an imaging matrix or an imaging system. So let's see what happens here. Let's do it, because I have done it, and I'll do the math for you. Okay. So we had a certain, I'm using SO instead of DO here, but I said, let's be at a certain distance, DO, SO. Let's go through a certain thin lens with a focal length of F. And then let's propagate by a distance that I don't know yet, but SI. Okay, I multiply the matrices. I start with the first on the right, this matrix first, this second, and this third, and I multiply the matrices. Okay, at that point, it's just math. I'm just multiplying matrices. Okay, multiply this times this times this, and I did it. Okay, so when you finish the multiplication, you just get this. Okay, blah. Okay, so just at that point, it's just a technicality. Multiplying matrices will give this. So far, so good? Julien,
Yes.
Valérie, Vincent, especially?
Yeah.
Okay.
Yep.
And what did we say? Okay, so that's starting at the object, going through a lot of things, and then ending at what I hope will be my image. So what do I want? I want the B element here to be 0. Okay, so what do? I do, okay, I'm taking this B element, SO plus SI times this, and I want that to be equal to 0. When is that equal to 0? So I have SO plus SI times SO over F with a minus sign plus 1 is equal to 0. Well, I manipulate this equation a little bit. And so I multiply everything by F. So I get SO times F minus SO SI plus SIF equal to 0. You understand that this is the same equation as this? Everyone?
Yep.
Yeah? Not sure?
Yep.
Valérie?
Yeah.
Okay. And then if I divide this by SO, SI, and F, what do I get? Kawabunga. I get, okay, I get an equation that I probably recognize that tells me that the distance to the object and the distance to the image is related to the distance of the focal length. So I would just isolate this. I can just isolate this, and how do I do that? It's 1 over f minus 1 over SO. That's equal to 1 over SI. So therefore, SI is 1 over minus 1 over SO, like this, right? So I can calculate the image, the position of the image, just from the position of the object and the position, not the position, but the focal length. What is the, okay, why do I care? Why do I care? Because you said, wait a minute, I knew this when we started, and you just made it more complicated. That may be what you're thinking. You're thinking, I knew this, and this was simple, and now I have to multiply matrices and remember. Blah, blah, blah. No, there is a reason, because this equation that you know works when you have a single lens and a single simple thin lens. What do we have in real life when we do microscopy? We have objectives. Objectives are complicated. They're very thick. They're not thin lenses. So what I will show you in when we continue after the break is we can take this will be relevant and will be sufficient. But what we'll do is that we will tackle weird systems, complicated systems, but we will simplify them so that this equation here, 1 over dO plus 1 over di is equal to 1 over f, this equation will still apply, but we will measure the distances from what we will call principal planes. So what does that mean? That means that we'll take a funky lens, replace it, and say, yeah, it's complicated, but it's as if this was a lens that started here and finished here with a focal length of f. So we'll just take a complicated lens and replace it by a broken lens in parts. Well, we'll just say it's as if the entrance of the lens was here and the exit of the lens was elsewhere. But then this equation here will be valid. That's going to be awesome. And then we will be able to take a complicated lens and say, I don't care really what's inside. And actually, do we know what's inside an Olympus microscope? We don't. They're not telling us. They're not telling us what's inside. Does that mean we can't do ray tracing? No, it does not. We will replace the objective. We'll just say, I know what its focal length is because I know it's a 20x objective or a 40x objective. We know what it is. We'll just say, all right, I don't know the details, but it's as if I had this focal spot at the front, this focal spot at the back, and something happens in between, but I don't know. So we'll replace an objective, thanks to the matrix formalism, by the equivalent of a thin lens. Okay, so all right, so this is really the time to take a quick break, and I'll try to figure out how we can put all of that together. But let me finish with my last slide. That ABCD formalism is super general, okay? And we still need to remember the simple cases, the simple lens, the simple interface, the focal length of a system will always bring everything back to a simple lens. But without the formalism, we wouldn't be able to do it. And then we'll be able to do tons of other things and replace actually very funky systems without knowing what's inside. All right, we take a break. I really need water, but I really need water. But we have all the things that we need to remember here. Was it understandable?
Yes.
Everyone?
Yeah, absolutely.
Yeah. Okay.
Yeah.
All right. So let's take a break. I'm really, really thirsty. It's not wine o'clock yet, but it's coming. Okay. All right. So maybe a little bit more than 5 minutes. Let's come back here in a little bit more than 5 minutes. Ta-dam.
Hello.
Hola. Okay. All right. Okay. Sorry for the delay. I had to wrestle with my son. He's trying to learn how to get out of a full Nelson. The full Nelson is a very difficult move. Okay. All right. Where are we here? Yes. Okay. So, is everyone here? Valérie, Vincent, not here? Oh, let's wait a little bit. Unless they're here and it's just that we don't have their cameras. Vincent? Valérie? Yeah, okay.
Hello.
Ah, okay. We have Valérie. Now, Vincent, at some point. Okay. Well, we'll just start again because anyway, well, we need to start. Okay. Okay, so I hope that you have appreciated how powerful the formalism is, and we have done several examples, so you should be able to use it in simple examples too. Okay, so I will just do 3 examples very, very, very quickly. Without going in more details, I'll just go very quickly so you can see certain things that we can conclude when using the formalism. For instance, we'll do 2 lenses stuck to each other. What happens when we have 2 lenses stuck to each other? You know, one after the other, one lens, another lens, quick, almost touching, essentially touching. And then we'll see what happens if we do a 4F system. You remember last week we talked about the 4F system?
Yeah.
Hi, just a sec. Hydration. Okay, so we'll do the 4F system with this formalism. We shouldn't be too surprised of what will happen. We'll see. And then we'll move on to we'll generalize. Okay, so let's dive right in. So what happens if I have 2 lenses, 2 thin lenses stuck to each other? Well, let's just multiply the matrices and see what happens. So I have first, I have a lens. Well, I should draw it. I have a lens with a focal distance 1, and right next to it, I have another lens with a focal distance f2. Okay, so this is the first one is represented by the first matrix. The second one is represented by the second matrix. We multiply the matrices. What do we get? We get this 1 over f1 minus 1 over okay, 1 minus 1 over f2 with a minus sign. What do we get? We get this. Okay, so we get a new expression. What's this new expression? The new expression is, it has essentially the same form as a thin lens, but we have added, it's as if the inverse of the focal lengths add up. Okay, because this, if I take this, I can rewrite it. I should have done that on the figure, but I did not. But I could rewrite it as 1, 0, 1, 1 over f1 plus 1 over f2, like this. 1. Do you see that? Everyone sees that? Okay. So isn't that interesting? Okay. So when do we? There are 2 things that you know from this. When do we sum the inverse of things? When have you know that from other fields? Resistances in parallel and in series. It doesn't matter, okay? It doesn't matter. The point that becomes important is that we can, it looks like the focal distance is something that means something to us. You know, it's a distance. We say, oh, yeah. If the focal distance is 50 millimeters, then from the lens to the focal point, there's 50 millimeters. So it's something that means something physically to us. But the thing that makes more sense in the math is the inverse of the focal length, because that exists, okay? It's called the power of a lens, okay? The power of a lens, whoops, is minus 1 over f. So then, I'm sorry, it's 1 over f. So if you have two lenses that are right next to each other, you add their power. Okay, what are the units of power for a lens?
1 over meter?
Yeah, 1 over meter. So do we know that? Do we think we know that? Have we, what is there another name for 1 over meter? I'll tell you. Diopters. What are diopters again? So when we say, I say that my lenses, I'm myopic, and I have 2. That's 2 diopters, or 2 meters minus 1. So Vincent, for instance, is not 2. Vincent is probably more like 7. 7?
No, but I don't know.
And you don't want to know. So the power of a lens, or that's why we say my glasses are weaker than Vincent's glasses, because they're just 2 diopters and his are 7 or something like that. So the power of a lens in diopter is a very standard measure in real life. When we do lasers and optics in the lab, we don't speak in diopters. Who does that? No one. But when you talk for glasses, then it's a very convenient unit. Okay, second example. I like to do it. I like to do it at this point because it's very useful for the next page. But let's just assume I want to propagate from one focal plane to the other focal plane. Okay, I don't need to tell you why I want to do that. I'm just telling you that I want to do that. So I'm going to start, I'm going to start from here, the focal spot on this side, or the focal plane, really, and I will go on the other side at the same distance at the other focal plane, right? Okay, that's easy. That's easy. We can do that. How do we do that? Well, we propagate, we start here, then we propagate a distance f, and then we go through our thin lens. I noticed that it's, yeah, okay, I'll move, whoops. It's been moved like this. Okay. I'm just fixing my figure. There we go. It should move on the drawing at some point. Yeah. There we go. All right. Okay. So I go from here. I move a distance f. Then I go through my thin lens. And then I move a distance f again. Okay. We multiply the matrices. Just notice that it looks like this. Okay. It looks like this. So that means that if I have a certain y theta at the entrance, I will have at the output f theta and minus y over f. Okay. I'm just pointing at one fact. The height of the output beam depends on the angle only, and the angle of the output beam depends on the height only. I'm just saying, okay? So for those a little bit more mathematically inclined, okay, this and others just don't listen, but in a more general Fourier discussion, when we discuss optics, very often we discuss in terms of Fourier components, and we will say that the angle and the position are two Fourier variables. So the lens going from here to here exchanges the position and the angle and the position. It interchanges them. It does a Fourier transform when you go from here to here. It's an optical Fourier transform. Okay, zoop. Okay, stop. No more. Okay, we stop here. Okay, but so we know that it's a reverse diagonal. It's not a diagonal here, but it's a diagonal here. And it's a very, 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 very common component in optical systems. Okay, so now, well, let's do the 4F system. But what's the 4F system? The 4F system is going from the focal plane of the first one to the lens to the focal plane on the other side, and then to the lens, through the lens, and moving another distance f2. So there are two things we can do. Of course, we can multiply all the matrices, do propagate a distance f1, then a lens f1, then another f1, then f2, then another lens f2, and then another f2. Or we just did on the previous slide, we know propagating from one focal plane to the other, we know that answers. We know that answer because we just did it. So we can take, we know that going from focus to focus, we know that 0f minus 1 over f, 0. So then it's simple, and I save a lot of time. And I say, well, okay, that means I'm propagating here from the focal spot of the first one to the focal spot of the second, and then the focal plane of the second to the focal plane of the second. So when I multiply these matrices, what do I get? I get this interesting diagonal matrix with minus f2 over f1 minus f1 over f2 here. What does that mean? What does that mean? That means that if I have, it's drawn here, okay? Look here. If I have, okay, I did the multiplication, multiply this by some input r theta or y theta. What do I get? I get an r prime and theta prime that is given by minus f2 over f1 times the original r and minus f1 over f2 times the original theta. How is that a surprise? Well, that's not a surprise, because what is a 4F system? What does the 4F system? The 4F system takes an object and makes an image with a magnification of f2 over f1 with a minus sign. Huh. Hey, recover, poof, 4F system in a line, okay? So what do we have? That means, well, that means we have our 4F system. The 4F system is just a diagonal matrix with minus F2 over F1 minus F1 over F2. Why the minus sign? Well, because
it is inversed.
it inverts the image. It inverts the object. So we have the object here. If there's a point at a given position 1, at a given height 1, then on the other side, it's minus 1. Okay? And then one final thing that I didn't take the time to explain in great details, but do you notice that, let's say, if you have here, if R, I don't know, do I have that on my next slide? I would like to have that on my next slide. Let me take a look. No, I don't have it. Okay. Yeah, okay. If F2 is larger than F1, then the object will make an image that is bigger.
Larger.
And what happens to the angles? So do you see, it may not be obvious to all of you, but here, let's say I have several rays. Let's say I have a ray that makes an angle. Yeah, okay, I'll just draw one. Yeah. Let's say I have a ray here that makes an angle theta. What angle is it going to make on the other side? Whoops, on the other side here.
My F1 or F2 theta.
It's going to make an angle that the height of the object, let's say, okay, let's assume for the discussion that F2 is 20 and F1 is 10. So this 4F system expands the beam by a factor of 2 in distances. So F2 divided by F1 is 2. So for angles, what do I get? F1 divided by F2 is half. So that means that if a ray makes a large angle on the object side, it makes a small angle on the image side. Okay, that is actually important, and it does have a lot of impact in your projects, all of you. Okay, anytime, let's say, the impact of this is that if you have an object that you're trying to make bigger, the beams, if the angles of the rays that are coming will be smaller. But the other way around, that means, let's say you have something that is big, and you want to make it small. You will have rays that will come with very large angles. So you can't have something that has, let's say you have something that is a certain size with a certain amount, a certain maximum angle. When you make it bigger, you reduce the angles. And when you make it smaller, you increase the angles. But sometimes you can't make it, sometimes these angles will not go through your system. Okay, so that is something that is actually important. And we'll see that in how many slides? In a few slides. Yeah, maybe more slides. A few slides. Okay, but Valérie, do you recognize that?
Yeah.
Okay, good. It's very relevant for Valérie's project. Okay, so what do we, what do we have? Okay, notice that if you make something bigger in size, you make the angles smaller. Okay, And example 3, yeah, okay. All right. Yeah, okay, everything that's written here is what I just said, So I'm not gonna repeat it. Okay, and okay, just to go back to things that we already knew, but you know, what's a 60x objective? Okay, what's a 60x objective? Does that mean anything? A 60x objective? It means nothing. It means, well, by itself, I'm sorry, Shadi. It does mean something, but it only means something because an objective is always used in a 4F system. So when we say 60x, we really mean that the focal length of this objective is 60 times smaller than the focal length of the other lens in this 4F system. That's what I meant. Really sorry. I really need to get something to drink. Okay, so just so you know. Okay, and I told you that there are 4F systems everywhere. Okay, now I really quickly want to get into we have the formalism and we've manipulated the formalism quite a bit. So we should be able to start generalizing what we've learned. Okay, let me get a glass of water because I keep, my throat is too dry.
No.
Okay. Okay. All right. Rock and roll. Okay. So you see on the screen now that we have discussed thin lenses, and I showed you that the formalism was general enough so that we could generalize for more complicated lenses. And the key concept that we need to learn is what's called the principal plane. So what I will show you in the next few slides is that we know the thin lens. But if we look at a complicated lens, a thick lens, okay, for now, let's just discuss the thick lens, but you'll see it applies to everything. A thick lens, for instance, is a microscope objective is a thick lens, right? So what we'll do is that we would love to be able to use the simplicity. There are so many things we know with thin lenses that we'd like to reuse everything we know. You know, for instance, a 4F system with thick lenses. You know, I completely, you know, skip that detail, but can you do a 4F system with a thick lens? Well, obviously you can, because I showed that we are making, you know, we're using this thick lens with some other lens, and for some reason, it's still a 4F system, and it still works. So obviously that's possible. So we'd like to know how to go from a thick lens to a description that is simpler, okay? And we'll do that with something called the principal planes. So we will replace this a thick lens by a new construct. Okay, I will show you how we will do that. But we will say that if you look at the figure here, we will say that, okay, just look at P1 and P2 on this figure, okay? But we have this complicated lens, and we will find something that's called the principal plane, the entrance principal plane, P1, and the exit principal plane. Non, j'ai pas bientôt fini. My daughter wants to play Fortnite on my iPad. OK, je vais te le dire quand je vais avoir fini. Je suis occupé et je parle à des gens. Ils disent que Fortnite, c'est poche de toute façon. OK. 1 heure. OK? That's not true. We're not going to speak for an hour. But I just wanted her to go away. Okay. So we will find something that will be the principal plane. What will the principal plane do? The principal plane will, we will assume, look at the blue ray on the figure. The ray enters the lens, and when it reaches the principal plane, the entrance principal plane, it's poof, teleported to the exit principal plane, where all of the power of the lens is considered to act. So then it focuses to the focal point. So that's actually fairly simple. We're just saying that this big thing, this big thing here, is if we just describe it in terms of its principal planes, we take this and we're changing it to some plane, some other plane, and the light comes in, zoop, and then zoom. Then it's focused after the principal plane. So that's easy. That's easy. And we'll see that we will define the focal length from the principal plane. So we'll just say that if this is the axis, we'll say the focal spot is one focal distance after the principal plane. Okay, that may sound a bit complicated, but for a thick lens, that will allow us to just discuss the lens with its focal length, and we'll just say, where are the principal planes? We'll just ask, where are the principal planes for a certain lens? But we can look at this in general terms. Okay, there's something else called the nodal planes. Okay, here, the nodal planes, but we don't need to worry too much about them, because in most of what we do, it's not very critical because they're equivalent to the principal planes. So for now, let's not worry about the nodal planes. Let's just worry about the principal planes. So here you have definitions, and the definitions that I wrote here are exactly what I just said in words. The principal planes are imaginary planes where all of the lens has its power, and a ray that reaches the principal plane will magically be teleported with a magnification of 1. So if it enters the principal plane, the entrance plane at a certain height, y, poof, it appears at the second plane also at a height y. However, all of the power of the lens is there, so it will change the angle according to the power of the lens. Okay, so that's the definition of the principal plane, and we will just redefine the focal length just a little tiny bit differently. Instead of, what did we say originally? We said, what's the focal spot? The focal spot is where a beam coming from infinity, a beam that's parallel, will cross the optical axis a certain distance f after the lens. But now we'll change it just a tiny little bit. Okay, we'll say the focal distance is, or the focal spot is one focal distance away from the principal plane. Okay, and the link here is that in a thin lens, the principal planes are really just at the center of the lens.
Mm-hmm.
So in a thin lens, what did we have? We had rays coming parallel and at the lens, or at the principal plane, the entrance principal plane. All of a sudden, all of the power of the lens at the lens is transmitted to the output principal plane. That's also at the center of the lens. And then it focused towards the focal spot. Well, in our case, it's going to be enters principal plane, sent to the output principal plane, and then focuses to the focal spot. So the principal plane and the focal spot are separated by one focal distance by definition. You know, it is just a more general definition of the focal distance. Now you may be thinking, why do I bother? You know, no one here will design microscope objectives. I'm sure, I very much doubt that you will, because I never did. Okay, so I've been doing optics for 25 years and I have never designed a microscope objective. So why am I telling you that? Well, it is relevant in real life when you have lenses that you buy, say, from Thorlabs. When you buy a lens from Thorlabs, you know, they will give you, let's say you buy a lens that is an achromat doublet. I'm sure people have bought achromat doublets. Well, an achromat doublet is not a thin lens. It's not thin at all. It's very often a centimeter thick, sometimes even more. So it's not a thin lens. So when you buy a lens and it says that the focal length is 50 millimeters, well, that doesn't mean that the focal point is 50 millimeters at the end of the lens. That's not what it means. It means that it has an effective focal length of 50 millimeters, but the principal plane is somewhere. That we don't always consider, or we don't always know. So let me just show you something that will be relevant to you. I think I'll do that here. I'll go quickly, just give me a second. I just want to show one example. It's coming. And it's here. Yes, this one here. Okay, I'll show you my screen. Do you see my screen?
Yes.
So do you see this here, the lens?
Yeah.
Yeah, okay. So what am I showing you? Okay, I'm showing you when you purchase a lens. This is a lens from Edmond Optics here. And when you purchase a lens, the lens has a real focal length. It has an effective focal length. So that's the F that we know. Okay, so on this diagram, if you have purchased such a lens, it will act like a lens that has a focal length of 100 on this diagram. But look at this here, okay? Look at the focal spot after the lens is not 100 millimeters after the vertex of the lens. That's not where it is. It is 100 millimeters after the principal plane. But we don't know the principal plane really. Well, we kind of don't. And what the manufacturers will provide is something called the BFL, or back focal length. So EFL is effective focal length, and BFL is back focal length. Now, that's a relevant number because the BFL on this diagram, and it's a completely standard nomenclature, okay? But if you say, I really need a focal length of 100 millimeters, and they'll say, there you go, here it is, the EO part number 33-921. It has an effective focal length of 100. But they will also give you the back focal length, the BFL, and that's something on their websites. Okay, on Edmund Optics website and Thorlab's website. You're back. Okay, so
Yes.
Yeah. Okay.
yeah. So I was saying the EFL and the BFL, they will give you the BFL on their website, the back focal length. So they will say, if you use our lens, you have an effective, it behaves like a lens that has a focal length of 100, but the focal spot on this for this particular lens is 78.3 millimeters after the physical, the end of the interface. That's a very relevant and pertinent information to know in the laboratory. So when you buy a lens, it's not always exactly F after, you know, the focal spot is not F after the last physical surface. It's really from the principal plane, which is not something that's given, and usually it's called the BFL. Okay, so let me just show you if we were to go to Thorlabs. You see my computer, right?
Yep.
Yep.
Acromats. Yeah, right here. Yeah, okay. So everyone sees that? I'll take one that I really like. Okay, the 1 inch right here. So do you see, whenever you look at their, let's say when you're buying a lens for your own setup, okay, so here, there's something, they say F with a little note A, and so at the bottom of my screen here, they say positive values are from the right side, blah, 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 blah. That's not what we want. We look at here, FB, and graphs. So we look at the graph, we click on, that's not what I want. No, that's not what I want. Where is it? It's not the one I want. It's going to be here. Overview and performance application. Where is it? Ah, where is it? I know. Ah, right here. Sorry. Okay. Okay. Ta-dam. Reference drawing. If you go here, there we go. Ta-ta-tam. So it looks a little bit more complicated than what I drew. Okay. But really, look here. Do you see my my pointer? What they're describing is FB for F back is really the position of the focal spot from the last interface. So that's the BFL, like I just described. And F is the effective focal length. So so for instance, if you look at this graph, okay, this lens here has a focal length of 30 millimeters, but the focal spot is 22.9 millimeters after the last interface. Sometimes that number, sometimes there's not a huge difference, but sometimes there is, okay? So it's something that you need to know when you design a system, because let's say if we don't do that much in academic labs, we don't engineer the mounts and get everything, you know, manufactured in a shop. But if you do get things manufactured in a shop, then you'll say, okay, put this lens here. Well, you need to know the real distance between the last surface and the the camera, for instance, where you really want to have your focal spot or your focal plane. Okay, all right. So I thought this was relevant, so that's why I discussed it. Oh. Are we?
Just a question. In our calculation, we use the effective focal length, yeah? Just in experiment, we use
Yeah,
back
exactly.
focal length.
Exactly. The
Mhm.
where's the yeah, okay, let me go back to my yes. It's coming. Yeah, okay. So okay, I'm looking for my slides. Where are they? Yeah. So the yeah, I need to skip ahead, and I don't like that. Okay, let me. When you have a system, you will have an effective focal length. Okay, you will have an effective focal length. That's the focal length we care about. That's really F as we want it. The BFL is really the relevant information you tell someone to say, the focal spot is physically here, because we don't give the principal plane position. It's hard. You know, if I were to tell you the principal plane is inside the lens by 3.2 millimeters, that's awkward. You know, it's very difficult. It's much more relevant to give it from the last physical distance. So the 1 over F that we put in the equation is really the effective focal length, because it behaves like a lens that has that focal length. Okay, we'll just do. I just want to do the principal plane calculation, and then we'll stop here because it's been a very long day. But what I want to do before we leave and before we all die is I will take an arbitrary system like the one we have here. Okay, you see, what do you see? You see my iPad screen?
Yep.
Yeah, this?
Yeah.
Okay, so I will take an arbitrary system that I don't know what it is. Again, we'll just say, it's ABCD. I don't know what's in there, but I will describe it as a lens. I'll just say, all right, I don't know what it is, but I will find these planes that are called the principal planes, and I'll find an expression that will tell me where they are, and that expression is going to be general enough so I can use it in all of my problems. So then when I have any system, the first thing I will do in a system is always to find the effective focal length of the system and the principal planes, so I can take the system and replace it by a single lens. This will always work. Okay, so let's do that, and hopefully it's going to take me just 7 minutes, and then we can all go for dinner. All of us by Zoom. No. Okay. So I'm reminding you that whatever, if we have any system, any optical system with lenses and space, we say, all right, I'm starting, say, here. I go through a thin lens, and then a space D, then another lens, then another D2, then another lens, etc., etc. We can apply the matrices, and if we started here and we finished here, we're replacing this big block right here. We're replacing this big block by a single matrix, A, B, C, D. Okay? So, assuming that I have this block, I could always decide, well, let me start a certain distance before that block. So I will calculate I will start just before I get to this big block. I will move forward by a distance L, then I'll be in my block, and then I'll apply the big matrix, and then I'll propagate another distance L2. I can do that. I can do whatever I want, okay? So that's what we'll do. We'll take a system that we don't know what it is. It could be anything as long as it can be represented by ABCD matrices. And I'll just say, okay, I'm starting at a certain distance L1 before. So I'm here at a distance L1 before. So I move by a distance L1 to reach my big block. Then when this block, we know to propagate from here to here, I know that I only need to apply my matrix ABCD. And then I will propagate by a certain distance L2. What I want to do is to find this position here and this position here where these two planes, okay, I want to have these two planes be my principal planes. Okay, so I want to start at a position that I don't know yet and go to another position that I don't know yet. That the first position here is my entrance principal plane, and the output is my output principal plane. So I have this block, any block that my problem is given, my problem gives me lenses, distances, etc., etc. So I have one big block and I have its matrix that describes it. Then I'm trying to say, okay, I don't know where they are, but I will find a plane and another plane that will tell me when I go from here to here, I'm going from my input plane, input principal plane, to my output principal plane. So how can we do that? Well, again, it's the same thing as we did before. We start from this plane here, and we move a distance L1. Then we go through our big matrix, ABCD, whatever that is. And then we move by a certain distance L2. So let's multiply these matrices. It's not particularly complicated. We have the first matrix, the matrix ABCD, and the other matrix. We multiply, blah, 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 blah. We multiply matrices. That's just math. At that point, it's just math. And then we have two things. Well, first of all, we have a mess of a matrix because it looks like that's one element, that's another element, another one, another one. So we have a big matrix, but we hope that these two planes will be the principal planes. And what is the definition of principal planes? There are two things, okay? The principal planes are conjugate planes that image something at the entrance, at the exit, with a magnification of 1. That's the definition of a principal plane. So there really are two planes where an object, an image, are identical. So when I go from the entrance principal plane to the output principal plane, it's an imaging system with a magnification of 1. So how can I solve that problem? Well, that's not too difficult, and you guys are going to tell me. So I have this big matrix. So I have a bunch of things that I don't know what to do with that, but I want that when I go from L1 to L2, it's an imaging system. So what does that mean, imaging system?
We don't consider theta, and yeah.
Yeah, and
we
Equals
put the
zero.
y2 is equal to y1.
yeah, yes, two things.
Mhm.
So you have both of them, but mathematically, so we know that the height, whatever comes at a given height, will come out at the same height. Therefore, it's imaging. If it's imaging, B is equal to 0. So we know that this big element here has to be 0. The second is the second thing you said. I said it's a magnification of 1. What is the magnification in this matrix? I don't think I've said it before, but
A.
E plus CL2.
yeah, exactly. That element here, because if I have a certain element that's say y1 theta 1, and I have A0 CD, because it's an imaging system. So what do I have at the exit? I have A, Y, something, something. So if B is equal to 0, it's A times Y. So the output Y is A times Y. So A, the element A, is the magnification. And the element B, when it's 0, it's imaging. All right. So we have two small equations. And one of them depends on the L2. The other one depends on L2 and L1. So we can simplify. It's actually not too complicated because we need to have A plus CL2 is equal to 1, which simply means that L2 is 1 minus A over C. And then just a little bit more math, but then we can replace L2 in this equation. And then we get that L1 is 1 minus D over C. Okay, that's a lot of math. Okay, what do we do with this? Okay, what is the conclusion? The conclusion is this. Okay, I did the more general case with, yeah, okay. I'll rewrite it here. It's going to be simpler. So L1 is 1 minus D over C, and L2 is 1 minus A over C. So L2 is 1 minus A over C, and L1 is 1 minus D over C. What does that mean? I had a completely general system. Okay? Super general system. And I found that there were two planes that are the principal planes. And they are, one of them, the input plane is at 1 minus D over C in front. And the output plane is at 1 minus A over C on the other side. So any system I can replace by, I have a big matrix, and I'll just say it's as if there was a thin lens that started L1 before and magically transported everything to L2 on the other side. And I don't have time to prove it, but I'll just tell you. But C, the element C of the matrix is always minus 1 over F. So the element C of any system is always the inverse of the focal length. So I have everything I need then for any system, okay? Because that means, forget about the nodal planes. They're not important in what I want to say. So we know where the principal planes are. And if you do a little bit of math, you can go read the slides, okay? But you find very quickly that the element C is minus 1 over F, always. So we have a lot of things now. If we have any system ABCD, we know that we can say, oh, if C is not 0, that means there's some lens power in that system. And if there is some lens power, then we can say it's as if it was L1 before, L2 after. So we're taking, think about it, we can replace an entire, 50 lenses with distances, mirrors, etc. We can replace the whole thing with, oh, it's as if you were one lens. That's awesome. That's really, really useful. That's really useful. And you have that in the assignment, by the way. But it removes, or it bundles all the complexity it simplifies everything into, it's just like a lens. And you'll have that in all of the systems. It always works. So the only thing you have to be good at for this, okay, but notice, by the way, I'm talking to biologists, there are no complex numbers. There are only 2x2 matrices that are not so complicated. And it's just 2x2 matrices that are not so complicated. So really, you really have something that's not so hard to master. And who had time to take a look at the video that the ray tracing videos that I sent? Okay, so if the beauty of all this is that now that you know how to do it, it's actually, you don't really need to do it all the time by yourself. Because if I have a computer program and I say, I want to go from here to here, well, you can take a Python ray tracing program and say, well, it's free space, it's a lens, it's free space, it's some other lens, it's a big lens, it's a small lens, whatever, blah, 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 blah. And then you can say, oh, please, can you give me the effective focal length of this block of stuff? Well, it can. It will multiply all the matrices, and then it will give you the element C of that matrix, because C is -1/F. So then it will give you F. Or if you say, wait a minute, where's the focal spot? Well, what will the computer program do? You give it a bunch of things, and it's going to say, oh, you want to know where the focal spot is? All right, I will need the focal distance. It will calculate the focal distance from the C element. -1/F is the C element. And then it's going to say, okay, you want to know where the focal spot is physically? Oh, I need to know the principal plane. Well, I do know the principal plane because we just did the math together. So it will take 1 minus A over C. It will calculate these things, and then will tell you, oh, the focal spot, by the way, is here. So the small ray tracing program that I gave you access to will do a lot of these calculations for you. And I don't do these calculations myself anymore, really. I just use a ray tracing program. But there's no magic. Everything that it does is as simple as what I just described today. But that means that, for instance, if you have your own optical system, your own optical setup, you can model it with these ray tracing things. You can figure out what is the effective focal length. You can even model your own lens. Let's say you have a lens from Thor Labs, and you'll say, okay, well, what are the distances? Well, you can actually put the lens in the code and say, what is really where is the principal plane? So you can model your entire system with this modeling, with this ABCD modeling strategy. So I took 3 hours to teach that. I hope it wasn't too tedious, especially for our 3 friends, Valérie, Vincent, and Julien. Are you dead?
No, not at all.
No, it was manageable?
Not that bad.
Okay. But now there's an assignment. Okay, there is an assignment. I'm ready. I have quite a few questions. And I have all the answers, by the way, and they exist. If you were to look for them on the web, you would probably find them because I put all my stuff on the web. But please don't look for the answers first. Try to do it. But I'll give you the complete solutions for all of our problems, just so you know. And I highly recommend that you start manipulating a little bit with, I would say analytically, with the matrices a little bit. But very quickly, that's okay. You can go use the ray tracing program to explore and see what happens when you trace the rays. Does that make sense? Okay, anybody has questions? No? Okay, do you want a long assignment or a short assignment? How many questions do you want? I could give you, I have a set of 50 questions that uses ray matrices that I can give you. I have simple ones and complicated ones. So what I'll do, okay, because I think that Shadi Elahe and Emile can do more, muscular programs. So I will let you choose the problems you do. So Valérie, Vincent, and Julien, you don't have to do all of the problems. I'll indicate difficult. I'll indicate difficult with a star or something, just to give you an idea. And I wouldn't expect Vincent, Valérie, and Julien to do all of the problems. And same thing, Shadi, Emile, and Elahe. Some of them may be too simple, but that's up to you. And anyway, we're all home doing nothing, so you might as well do all of them. But I do have all the solutions for all the problems, so I'll send you that. And ideally, you could give that back to me Wednesday. I would prefer if you guys finished everything for Wednesday, because if we extend everything, then we'll just, it's going to drag forever. So I'm hoping that we can finish this for Wednesday. And if that's not possible, then maybe Wednesday night. But really Wednesday.
If there are 50 questions.
Oh, no. There won't be 50 questions. No. No. I'll give you 4 to 6 questions. But I was just saying that I've been teaching this optics for 7 years now. So I have a large set of questions that I can ask. Some of them are very difficult. Some of them are very easy. So I'll just pick and choose to give you things that are relevant. All right. And please use the ray tracing program. Who has never written a single line of Python code?
Sorry.
No, it's going to take you a minute. It's the same as MATLAB. It's like MATLAB, except that it's not. So everything will be fine. You guys will all be fine. Okay. So I hope this was useful and interesting. This is the part of geometrical optics I like the most, by the way, if it doesn't show. So I'll try to send you that. I still have an hour before dinner, so I think I have time to give you the problem set before dinner. Feel free to go back to the slides. I gave you the link to the slides. Go there. Feel free to modify, to help me with the slides. If you see mistakes, I even gave you edit access. So you guys could even modify my own slides. Translate them, improve them, yada, yada, yada. Okay, so, all right. Oh, yeah. One very, very small thing. This formalism is very general, but there's a tiny little subtlety in a few books, okay? And it's just so you know, because why am I telling you that? Because I didn't know during my PhD, and I made a mistake for a few years without knowing, so I'm telling you, okay? Some books will actually define, instead of saying r theta for the vector, for the ray, they will do R n theta. So they will, there's a reason for that. There's a very, very good reason to do that mathematically, but it's always going to be the angle times the index of refraction. That's not what I did. Okay, I really used, you know, R and theta, which is the book that I prefer, the photonics book from Saleh and Tech. That's what they do too. That's what I've been doing. That's what most people do. But there are a few books that that will have that will use n theta, and then the matrices will be a little bit different. So it's just something you need to know, because if you start, you know, just saying, oh yeah, I learned ABCD matrices with Danielle. I'll just look them up. You go on the web and you type ABCD matrix and say, yeah, there you go. That's the matrix. Well, you have to quickly double check what formalism they're using. Is it R theta or Rn theta? Okay. And one final word. There's even in 2 minutes, even if even in optical design, you know, there are a few optical designers at Laval. The group of Simon Thibault is the one that comes to mind, but they do a lot of optical design, and they don't use the ABCD formalism. They used another formalism called the YNU formalism, but actually it's really the same thing, because Y is the height, U is the angle, and N is the index of refraction. So really, this formalism is very, very, very general, and it can explain everything in the systems that are relevant to us. When you do a fancier description, then you can start describing aberrations and a bunch of other things, but we're not going to do that here. So I'm coming up with the assignment. I'll send that to you, and feel free to ask questions if that's not clear. All right?
Thank you.
Dynamite. Thank you.
All right, thanks.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.